Now, if a quadratic approximation, which is essentially a second order approximation, we've got two terms to make our approximation with, is a better, more accurate approximation than a linear approximation, which is a first order approximation, then a third order, adding the third derivative, would give us an even more accurate result. And in fact, we can add as many orders as we wish. And this is known generally as an n-order polynomial approximation. If we add enough orders, if we add enough terms, we can fit just about any expression. In the general form, this is sometimes referred to as a Taylor series expansion or Taylor's formula. And if we want to add as many orders as we want, it gives us an algorithm to follow. So notice that if we only take this part here, this is a linear approximation. If we take this, we get our quadratic. And you can see that it's written in general term. We've got 2 exclamation mark. 2 exclamation mark is just equal to 1 times 2. And n to the exclamation mark would be equal 1 times 2 times 3 times dot 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 times n minus 1 times n. So you can get as many orders as you want. Now, Taylor's major insight has to do with this error term here. And there's a way to measure the error term, at least approximately, and to get a bound on the size of the error term. So not only are you using an approximation that's easier to calculate, you also have an idea of how much precision your approximation has. So if approximation is important, say you're trying to send a rocket to the moon, or you're trying to send a Land Rover to Mars, approximation is going to be very, very important. Or I should say, accuracy is going to be very, very important. And a Taylor series expansion can tell you the size of the possible error. Now, you can look in the textbook, and you can see that the derivation is a couple pages long. I'm not going to cover it. We are not going to cover it in Econ 1530. It doesn't come up that often. I've never had to solve for this error term when I'm doing my research in economics. But I want you to be aware that it exists. What you do want to be able to do and remember is this part right here, which is like the linear approximation and the quadratic approximation we've done. I've done quadratic approximations. I don't recall ever having to do a third order approximation in class at any level or in my research, but it's good to understand the intuition because I've certainly read papers where people have. Now we've got another practice question, so we're going to do another quadratic approximation. This time we have a much more difficult function to actually calculate. And it's an implicit function. We've got y being an implicit function of x. So let's take a look at it. Now, the first thing to notice is that we are asked to evaluate it about, and maybe I'll keep that word in there, about x is equal to 0. Notice that if x is equal to 0, then this equation becomes 0 times y cubed plus 1 is equal to y, and we're left with y is equal to 1. So we're looking at evaluating this expression about x is equal to 0 or the coordinates 0, 1. Now let's write out the formula to follow for a quadratic approximation. So I'm writing it out in the direct function form, but we can change it around just a little bit so that we can use it with this implicit function. We've got f of x is not equal to, it is these curvy equal sign, an approximation around f of a plus the first derivative at point A times x minus a plus the second derivative at point A times x minus a, that's the change in x, squared. And it looks like I was so excited about the square difference in x, I forgot the 1/2 at the beginning. So to start, let's define each of these. F of a, well, what's y equal to when a is equal to 0? It's just equal to 1. That's what we showed up here. What is f prime a? So this is going to take a little bit of work. What we actually want to find is we want to find y prime when we take the implicit differential of this expression up here. So we're going to have 3y squared xy prime. A little bit odd the way I've written it, but that's okay. Derivative of 1 is 0. It's a constant. But of course we've got the product rule, so we're going to have y cubed there. And this thing is going to be equal to y prime. Now let's solve for y prime. And we get something like that. And then if I factor out the y prime, we get, and I don't know if I've, and then this thing, I could rewrite this. If I want to get rid of that negative in front, I could rewrite it as, now let's evaluate y prime at this x equals 0, y equals 1 point. So we're going to have 1 cubed up there, and we've got 1 minus 3, 1 squared times 0 in the denominator, and we get y prime is just equal to 1. That wasn't so hard, was it? Now to find the second derivative, let's go back to this term up here and let me duplicate it. And let's take the derivative of this again. Because we want to take the derivative before we start subbing into values. If we sub in the values first, we're not actually going to find the derivative. We're going to find nothing. So let's take a look at this, and I've got a product rule at the front, which is going to be a tricky one to deal with because we've got three products. So let's start with that one. All right, let's take the derivative. So starting with this term here, we're going to end up with, well, we'll take the easiest one first. So we're going to end up with 3y squared y prime. And then, well, we can take the derivative of that one, which is just going to be 3y squared x y double prime. Now we've got that one. We're going to end up with 6 y, x, y prime, plus 3y squared y prime equals y double prime. Woo! That's a lot. Now let's go ahead and solve for y double prime, the second derivative of y with respect to x. And I want to collect those like terms together. So we're going to end up with 3y squared x y double prime minus y double prime is equal to negative 3y squared y prime minus 3y squared, oops, my bad, take that out, minus 6yx y prime, well, I'll keep it as y prime times y prime instead of y prime squared, minus 3y squared y prime, and we're going to end up with y double prime is equal to negative 3y squared y prime minus 6yx y prime prime, oops, it's a plus now, plus 3y squared y prime, all that over 3y squared x minus 1. And I wrote this one wrong. I meant to just write another y in here. So it's y prime times y prime. And subbing in the right values, so I'll leave the negative sign up there. We've got 3 times 1 squared times 1. Here, this term is going to disappear because we've got a 0. And then we've got 3 times 1 squared times 1. All of that over 3 times 1 squared. Oh, 0. That one's going to be gone. Minus 1. And we are left with negative 3 plus 3 over negative 1, which is just equal to 6. So we have y double prime is equal to 6. Now we have everything we need. So we can approximate f of a as being equal to 1 plus y prime, which was 1, times x minus 0 plus 1/2 6 times x minus 0 squared and our approximation looks like 1 plus x plus 3x squared. Now what have we approximated? We've said, well, if I'm looking to find y around x is at some value, it's going to be approximately equal to 1 plus x plus 3x squared. So if you give me an x, I can give you an approximation for y when we have this very ugly function, which was, what was it, x? Y cubed plus 1 was equal to y. So if x is equal to 1, then y is approximately equal to 1 plus 1 plus 3 times 1 squared, approximately equal to 5. and I realized that I made a little typo. So we're not trying to approximate f of a. Of course, we're trying to approximate f of x at a. So this should be an x here. That's the general formula. We're trying to approximate f of x given a.